Okay, now we're doing the vectors topic, and we're going to have a look at equations of straight lines in this video. We're going to try and get you through all of the theory behind equations of straight lines, 3 different forms, 4 examples. We're just going to absolutely blast through it. So stay with me. You can zoom or find a place back or forward if you need to pause it. Jump ahead, but I'm going to try and go through it all in one because it kind of lends itself to going through all in one go. So what we're going to have a look at is how to express a straight line that goes through 3D space. I'm sure pretty well familiar with the idea of equations of lines in 2 dimensions, usually in terms of x and y, and we've got the general form. There's various forms of it: y equals mx plus c. We've got a way to relate a straight line in 2 dimensions. However, how do we come up with an equation to represent a line going through 3-dimensional space? We need to have obviously some reference to x, y and z coordinates. So that's what we're going to have a look at in this video here. There are 3 forms of the equation of a straight line, and these are the forms that are stated here: vector form, parametric and symmetric form. And they all have their own uses. The vector form is the starting point from which we can derive the other 2, and as I said, we use them at different points for different uses. There are usually 2 ways in which we're given information to create an equation, and it's fairly typical to probably your experiences in 2-dimensional equations of lines. You'll either be given a point on a line plus some information about the gradient or a parallel line to that, or you'll be given 2 points that the line passes through and asked to work from there. But the good news is that the kind of main ingredients that we normally use for 2-dimensional lines is still required, and that is something about a gradient and some information about at least 1 point. So that's the kind of information that we're still working towards in all of these different examples. Okay, so let's zoom on. First of all, vector form. And what we're going to have a look at is a definition of a straight line in vector form. So we've got a point A, which is a fixed point. Now, in all of our work, we're going to assume that we know the coordinates of A. A is the point which we know. So say, for instance, it's the point 3, 2, 1. And R is going to be the point that we don't know. It's going to be our reference point x, y, z. Now say there's a line that goes through A and R, this purple line, line L, and if we know that there's a vector D which is parallel to line L, then effectively D represents the gradient of that line. We know that D is going to be a vector with instructions in 3 dimensions. It'll have an x and y and a z component to it. So effectively, vector D becomes the gradient instruction for line L and any other parallel line to it. So if that's the case, we can say that if AR and D are parallel, then it must be true that the vector AR is actually a multiple of D. And we're going to introduce a parameter T. T is some kind of real number, but T is our parameter, multiple. So what we can say is, because they're parallel to each other, hopefully you know of vector quantities. If they're parallel vectors, then they have to be some kind of multiple of each other. So that's a true thing there. And if we have vector AR, we can represent that by position vectors R and A, and we can come up with the little equation R minus A equals T, some scalar quantity multiplied by D, and a little rearranging of that will give me R equals A plus TD. Now remember that R is our x, y, z position vector, and A will be a known coordinate and D will be a known vector which represents the direction. So really, that is the equation of the line in vector form. And you might be given information about all of that, and I'll give you an example just in a moment. So that's basically the layout of the vector equation of the line. So for instance, example 8, find the vector equation of the straight line through a given point parallel to some vector I plus 2j minus 8k. So what we're saying here is that we have some kind of point A, which we're going to nominate as 2, negative 1, 6. In other words, A here is 2, the position vector A is 2, negative 1, 6. And we're told that we've got a vector which is parallel to our given line. That's going to be vector D, the direction vector, which is 1, 2, and negative 8. So remember that our position, our vector D here, we actually call it the direction vector. That, in 3 dimensions, replaces the concept of the gradient of a line. Gradient we really keep to 2 dimensions. The direction vector replaces the gradient in 3 dimensions. So it does the same job. So I've got a point and a gradient effectively. So now I'm ready to find the equation of my line. I can say the equation of the line is represented by the form R equals A plus some parameter T times D. And we've got information that we can put into it if we need to. So R is equal to 2, negative 1, 6 plus T times 1, 2, negative 8. And that's it. That's the equation of the line in vector form. Remembering that R kind of really represents, and we're not putting it in really in this point, but R really represents the position vector x, y, z. Okay, you might see, certainly in textbooks, the vector form written in unit vector notation. It's really not particularly pretty, in my opinion. It's functional, and it's good if you can't actually write out column vectors on a page, but yeah, if you see it, don't panic. You can rewrite it in kind of column vector form that maybe looks a bit better. But that's the equation of the line in vector form, okay? Moving on, we want to then turn vector form into parametric form. Now, hopefully you remember parametric equations, for instance, are equations, or functions rather, are functions for which each of the x and y coordinates have their own function. So we introduced the parameter in a parametric equation, and we've already introduced a parameter into our vector equation. Therefore, we can, in a way, split the 3 directions x, y, and z into their own equation. So this time I'm going to fill out vector R with my x, y, and z as I was alluding earlier on. And in terms of the theory of it, we define vector A, which is the point that we know as being A, B, and C. And we define the direction vector as having components L, M, and N. From a fixed point of view, it helps us to make some kind of formula or rule, but we're generally going to use numbers for this. So if we put it into our equation of a line in vector form, then we get this equation here. That's the equation of a line in vector form. The only difference between that and the one in example A is I put in x, y, z in terms of the components rather than just calling it R. Okay, but there's a parameter t sitting there here. So what we can do is we can split the equation up into its three rows, and if you notice, the first one says x equals a plus tl. The second row says y equals b plus tm, and the third row says z equals c plus tn. Now in that form we have the equation of the line in parametric form. We will, as typically in any equation of a straight line, we will have numbers to put in here and here, because ABC and LMN are numbers that we'll know from our point and our direction vector. The x, y, z's and the t will remain as these variables, but that's how we then change it into parametric form. So as an example, find the parametric equations of the line through a point and parallel to another vector, so that's our direction vector. So what can we say here? We can see that if that's the point A, I'm going to just go straight to writing down A in vector form, 6, 3, negative 1. I'm going to define my position, sorry, my direction vector, D, as 2, negative 3, negative 1. Now I still need to construct the equation in vector form. So in vector form, the equation, we can say equation of the line still takes the form R equals A plus T D, which means that if we're expressing R as X, Y, Z, A as 6, 3, negative 1, and D as 2, negative 3, negative 1, then we've got our vector equation. Okay? But we have to do that in a way to then construct, in this, at the moment. You might find there's another way later on. So to write it in parametric form, all we're going to do is then we're going to slice that equation into 3 bits and say in parametric form x equals 6 plus 2t. Note that I've changed the t and the 2 around just for normal convention. Y equals 3 minus 3t, and z equals negative 1 minus t. And that's the equation of the line in parametric form, where I've got 3 different equations. You might see some equations in this form being written out with the variable first, and that's fine. Quite often we write equations with variables before constant terms, just so you recognize that the information still has to be correct. That's to do with the direction vector or the gradient, and this information is still to do with the point. As long as you can pull it out in whichever order they're in, that's the equations in parametric form. Okay? Now, just going to rub this out because we're about to look at the very last form, which is symmetric form. And basically what it looks at is the fact that because each of these equations has a common parameter t, I could rearrange each of those equations. Okay, so the first one would become t is equal to x minus 6 over 2. In the second one, if we make t the subject of the formula, we would get y minus 3 divided by negative 3. And in the third one, we get z plus 1 divided by negative 1. It's not as fully simplified as we would normally do, but you notice that each of these fractions represents the value t. Now we know that t has to be the same for each of these, which effectively means that each of these equations is equal to each other. We have an equality. And that's basically the structure of our third and final form, which is symmetric form, sometimes called Cartesian form. So, rearranging the parametric equations, we end up with three little fractions, and it's really important to note that when we rearrange it, we always keep the x, y, and z variables positive and unitary. So we don't ever make them multiples, we don't ever change the signs in front of them. And you also notice that we don't need to simplify a denominator. We don't simplify the fraction, multiply through, we just leave the numbers as they are. And because each of them has the common value t, then we can actually stick them together. I normally kind of put a little equals t as a reminder to myself that we can split them back up again if we need to. And that is the form. This box here, this is actually what we call symmetric form of the equation of a straight line. It's the easiest to work with, and it's easiest to put information in and to extract information from. Okay, so I'll show you why. Here's an example here. There's a few parts to it. So find the symmetric form of the equation of the line. So we've got two different ones. So we've got a point 4, negative 1, 3. So I'm going to call that A for the first example. 4, negative 1, 3. And we need a direction vector, and we're given it as very explicit. We don't have to do any work here, nice and easy. We've got A and we've got D. Now, although we could go through the idea of making a vector form into symmetric and then into vector into parametric, then into symmetric, we can actually just use the template for the equation of a line. So all we need to say is that the equation of the line is as follows. The shape is that it's got x minus something over something equals y minus a number over a number equals z minus a number over a number, and that's all equal to the parameter t. Well, what are the numbers that go where? Well, looking back to here, we can see that the numbers on the top, A, B, and C represent the point that the line passes through, and L, M, and N represent the direction vector. So, the direction vector in our first example is 2, negative 3, 5, and the point is 4, negative 1, 3, so 4 goes here. The negative 1 makes it y plus 1, and the 3 here makes it z minus 2. So by default, it's x minus, and if it's a positive coordinate, it becomes x minus 4. The negative coordinate here, negative 1, note makes this y plus 1. But the good news is that's the equation of our line. We don't need to do anything more. We've already constructed the equation of the line in symmetric form. Have a look at B. Find the equation of the line through the point negative 2, 4, 0. So A is negative 2, 4, 0. Parallel to the line. Now, this time we've actually got our information in another three-dimensional line. So it's about knowing where to look for our direction vector, and of course we're looking at the denominators here, 2, negative 1, and 6. So we've got D is 2, negative 1, and 6. So just like we did before, we can already construct the template. The equation of the line, x minus something, y minus z minus equals t. So what do we need? We need a point on the numerator with the x, y, and z. So it's x minus negative 2, so that becomes x plus 2, y minus 4, that's the y component of A, and then the z component is 0, so effectively it just becomes z rather than z minus 0. Tidy that up. And the denominator is just a direction vector, 2, negative 1, and 6. that's how to find the equation of a line in symmetric form. Okay, so I'm going to leave it there. There's one other example using symmetric form because it's the most common one, but that's me basically covered the three forms of the equation of a line, how to find them, how to write them down, and I hope that's useful. So go on and have a look at example 11 and then practice yourself.